Hi, this video will cover section 3.5, exponential and logarithmic models. Um, this is the last section of chapter 3, which is about exponential and logarithmic functions. And this is a chapter where we're going to put everything that we learned in the previous sections into practice to solve word problems. So the objectives, we're going to recognize the 5 most common types of models involving exponential and logarithmic equations or functions. Use exponential growth and decay. Remember, I told you that was increase, exponential decrease. So we have words for that, growth and decay. Functions to model and solve real-life problems, and use Gaussian functions to model and solve real-life problems. And then we are going to have a new type of function, logistic growth functions, to model and solve real-life problems, and then finally use logarithmic functions to model and solve real-life problems. So everything is about solving real-life problems. So we have here the equations that we will be using, and what you see here are the mathematical models, just kind of like a parent function. So it's a parent function is the function, but in its simplest form. And what we have here for the models is just like a base for you to use, a model to use to construct your own exponential or logistic or logarithmic or Gaussian equation. So the first one that we have here, it is the exponential growth model, and we could see that it is growth because we're saying that the exponent, which is positive, is greater than 0. And then you could see it here. So if you have a positive exponent, you will have exponential growth. Here, the base is the number e, which remember is approximately 2.71. And then we have exponential decay, which is whenever you have a negative exponent there. And we know it's negative because b is positive. So if you put a negative sign in front of a positive number, then you will have a negative exponent. For this one, also e is the base of the function. And the letter A is actually representing a number as well, a real number. And that could be a number that it is bigger or smaller. It could be positive, it could be negative, and also it could be bigger than 1 or smaller than 1. Then we have the Gaussian model. And for this one, we're going to do an example. I don't know if you have ever heard about the bell curve. And in statistics is used to analyze several things. And we're going to look at one of those formulas, the normal distribution, with the example. And then we have the logistic model. And so the logistic model, it is kind of like an exponential and then combined with a constant function. So we will see the graph, but something that will grow exponentially and then perhaps like leveled up. That will be a logistic growth model. And then, of course, we have the logarithmic models, which will have ln or log. Here, the independent variable will be x, and what you see here for A could be a vertical shift, and then B is it will be multiplying, so it's like a coefficient of, in that case, ln x. So if it's bigger than 1, it could be a vertical stretch. If it's smaller than 1, it could be compression. So all those little numbers, of course, they do have a meaning, and so we're going to look at one example of each of the models. So here are the graphs. So we have the graph of exponential growth. You could see how, and this is for the function e to the x, you could see the y-intercept is there, and then it is increasing, so we call it exponential growth. Remember, we always read the graphs left to right. So the next graph is decreasing, and in this case we refer to it as exponential decay model. And so it will be there. Here's the equation. And the next graph that we have here is an example of the Gaussian model. So if you notice, we do have that graph that looks like an upside down bell, and that's why they call it the bell curve or the normal curve, if it is the normal distribution. Okay, so let's go here. Here's an example of the logistic model that I was telling you, that it could grow rapidly like an exponential, and then eventually it starts leveling. And of course, we will also revisit the concept of that horizontal asymptote. We also have the natural log. That's the graph. So we have a shift of 1 unit up because we have this 1 right here. And then common log, which is base 10. So remember, this is base 10. And this is base E. We don't need to write it, but I just want to remind you that that's what we do. So here's the graph. And of course, you are, if you have to do graphs for this section, I don't think so, but if you do, you're welcome to use your calculator or Desmos. All right, so let's start with the first example, and it says it's about online advertising. So estimates of the amounts in billions of dollars of U.S. online advertising spending from 2011 through 2015 are shown in the table. So we see here for those particular years, the advertising spending is in billions of dollars. So we have for the year 2011, 31.3 billion, 2012, 36.8 billion, 2013, 41.2 billion, and so on. So a scatter plot of those of the data is there here. So that point right there that I circled, actually I'm gonna highlight it. That will be the point that comes from here. However, I want you to notice how the x-axis, it says that the year 2011, we're just going to use 11. So we're only going to be using the last 2 digits when we graph it. So for the next point, it will be 12 for the x, and then for the, so imagine this is your x, your y, or your independent, that's better, and your dependent. And so that point will be here. And then for the next year, 2013, we only use 13, the last 2 digits of the year. And then we use the 41.2, so you could see it there. And of course, we have for the year 2014. So we have our point. And then finally, the year 2015, we only use 15 for x. And if you notice with the y-axis, or in this case, they're referring to it as S. And so S is going to be in place of the Y. Let's correct that here. So let's go ahead and correct that. So the year is T. lowercase t, you could see it here. And then the advertising spending, we're using the letter S. So remember, still, this is your input. T is your input, and your output is the advertising spending online. Okay, and here we're kind of lucky because we're getting the model already, so we don't have to find it yet. And then you can see how T, the years, is defined from 11 to 15 because we only have data from the year 2011, so that's why it says T is greater than or equal than 11, and also T is less than and equal to 15. So including 11 and 15. So in S, make sure you remember that it is in billions of dollars. Okay, so we're going to compare the values given by the model with the estimates shown in the table. According to this model, when will the amount of U.S. online advertising spending reach 80 billion? So we're going to use the next slide to do that. And so from the table, you could see how the model, which is the equation that we got, I'm going to write it here again. The model is the equation S equals to 9.30 e to the power 0.1129 t. And so if we want to find, the question is again, when, so it's a question about time, when will the amount of US online advertising spending reach 80 billion? So we want S to be equal to 80. And we do not need to add all the zeros because remember, we already have these numbers in billions of dollars. So we're going to do that. And we will start by substituting S with 80 billion. Just 80 actually. Then we have this equation on the left. I'm just going to copy it. Okay, so first thing we will do is take the 9.30 and we're going to divide that. It says here divide each side, so you can do that. I already know it's going to cancel out on the left, so I'm not going to do that. And so I'm just going to divide the right side. So 80 divided by 9.3. Okay, then we're going to take the natural log on each side. So natural log here and also here. And we have here e to the 0.1129 t, and then here we have 80 over 9.3. So we took the natural log because we have a base of e here, so we wanted to cancel that out, but it also is also a good way to solve any exponential equation. So we are lucky we can cancel that. So now we have 0.1129 t is equal to the natural log of that fraction. And you don't need to enter this in the calculator because you don't want to round too soon. And so from here, what we're going to do next is solve for t. So you could see how the number 0.1129 is multiplying to t. And so what we're going to do is take it across the equal sign and it will be dividing. So 0.1129 29, and that will be the value of t. So if we enter all of that on our calculator, let's see, it will, okay, so I am getting an approximation of 19.06. So if we had to round to the nearest year or whole number, we could round this to 19, right? And so since the year 2011 was t equals 11, then for this type of t, the year that we're talking about is going to be 2019. So in that particular year, the online spending will reach 80. And this happened last year, right? So maybe we could Google it and see if it was true. I mean, I imagine now for 2020, it's even way bigger because we're all online all the time. So, yep, that's a pretty big business to go into. Then we have here exponential growth and decay. Well, first of all, before we move on, this problem, if we were to graph it, it will definitely be exponential growth. And you could see how the y values, they are increasing. However, I forgot to mention that here, the numbers that come from the second row of the table are the numbers that were here on the table. You could see that. And so what happened here is the numbers were entered into a regression calculator, and that's how the model came here. So, but if you were to graph, so what we're going to do, I'm going to show you how you can go from the data given from this points in fact, I'm gonna oops, here we go. So I'm gonna show you how to find that exponential regression, because that is what you will be doing for your quiz number 4. You are going to construct a model using technology. So I just Googled exponential regression calculator. I'll share this link with you. And so I want you to ignore the numbers that are here. We're going to be deleting them. So I'm going to be entering the numbers. So for the X, because it's the independent, we will be entering the year. But remember, we only use the last 2 digits. And for the Y value or the output, we'll be entering the numbers that I have highlighted in yellow. So and the rest we're gonna delete them. So we start here with 11, and then for the y value, the value from the table was 31.3. And let's see. So then for the next number, we are gonna have 12, and then for the independent one, we will have 36.8. Then for the next year is 2013, but we only entered 13. And then for the amount of online spending, we are going to have 41.2. Then for the next year, it will be 2014, so we only enter 14. And then here we will enter 45.5. Then the last data set or point that we have will be 2015, so we just enter the number 15, and for the y value is going to be 49.5. Okay, and the rest we are just going to delete them. So I just simply press on it, and I think I can just do that. Or you could use your keyboard to delete them one by one. So this is how you will be doing your quiz. So I'm going to pause the video and finish deleting them. So I finished deleting the spaces that we were not going to use. And now I'm gonna press where it says execute. And because, actually, before I press it, we are in the E exponential regression, there's another type of exponential regression with the, instead of E, we will have the base A. I'm sorry, base B. And then A will be just a constant, not being raised to the exponent, only B. So we could do either way, but I'm just gonna try to stick to the one that we have on the book. And so I press that. And you could see the model is going to come from the numbers that we have here. However, okay. So here's the label. I'm going to zoom in a little bit. And so it says A e to the bx. And so if we get those numbers from here, A is equal to 9.29. And then there's an 8 and 8 after. So that tells me that it rounds to 9.30, right? According to the model, it says like A and then E and then B and then X. So we're getting that coefficient of 9.30 if we round it to 2 decimals. And then we will have E to the power bx, and the value for B right here you see is 0.11289. 0.11289. So if we round to 4 digits, it will turn into 0.1129 and then T. So that is how the model was found. However, not all these points from the exponential, from the table fit into the exponential regression. So what the exponential regression does, it just calculates the best fit for all those points. However, you could see how some of those are off. In fact, all of them are off, some more than others. For example, probably 2015 is the one that is off the most by 1.1. So what I did is I typed the equation for the model into Desmos. And so we have the graph here. And what I'm going to do is just to give you a better image, we're going to go to graph settings, which is the little wrench. And we're going to change the x-axis. Let's try from -1 and let's switch this to 25. And then we are going to change the y-axis. So let's start with, I don't know, -5. And then the highest, let's try 90. Or actually, let's try 100. So that will change my window so that my horizontal axis goes from -1 to 25. That will represent the year 2025. And our y-axis will be from -5 to 100. I just like to have a negative number so I know where the y-axis actually starts, or the horizontal axis. So we have the graph here. You could see it perfectly fine. And you could see how here at 80 billion, that's what we had to find using the model. Um, well, somewhere around that, around 19. And you could see all the points. So for example, year 2020, if this model was still true, the online advertising will be around 89 billion. So I don't know, it could be true. So what I want to show you from here though is the table. And so if we look at the table and I change these values from here to the years, so we have 11, we're going to have 12, we're going to have 13, 14, and 15. So if we get that, and let's do one more and enter 19. Okay, so if we get that, you can see the points are here. And so those are the exact values that come with the model. But if you look at the values from here, they match the values that we have here. So for the year 15, we have 50.6. Let's see if it's true with the table. 50.6. Yeah, if we round it to one digit. So as you see, the numbers are different, but that's because they came from the model, and the other ones came from the data that we had. So they could be a little bit off. Now, if you notice here on the exponential regression calculator, we have the coefficient r, and that tells us if there is a strong correlation. So the correlation tells you like how far off are the points, or if they fit nicely on the model, and if it's like a good match. So if you notice here, our coefficient is a 0.99. So since it is between 0.7 and 1, it is a very strong correlation. So that's why the numbers that you see here are not exactly the same per year. However, they're not too far off. So the model is a good approximation. Okay, so I know that took forever, but it's because you will do something like that for your quiz. Our next problem is about exponential decay. And we know it's exponential decay because we have the model here with a negative exponent, as you can see, -t. But before we solve that problem, we're going to go over some concepts. So in living organic material, the ratio of the number of radioactive carbon isotopes, we're going to have two types of carbon isotopes. One will be carbon 14 and the other one will be carbon 12. So they are just different types of carbon. And so the ratio that comes from one to the other in organic material, living organic material, including fossils, bones, or anything that contains carbon 14 and 12. So 12 and 14. So the ratio is 1 to 10 to the power 12. That is the ratio. So I'm going to use capital R to denote the ratio. And so when the organic material dies, carbon-12 content remains fixed. It doesn't change. But the radioactive carbon-14, it begins to decay with half-life of about, it's a little less than this, 5,700 years. So let's see what, let me give you an example of what half-life represents. So if the half-life is that amount of years, if you start with 100 grams of carbon-14, after 5,700 years, you will have half of that, 50 grams. Then those 50 grams, it will have to take another 5,700 years to be half of that, so there will be 25 grams. And then for those 25 grams to go half of that to 12.5 grams, you will have to have another 5,700 years go by. So in total here we have 17,100 years for 100 grams of carbon-14 to decay to 12.5. So as you can see, it's a pretty long time, and that is why scientists are able to determine the age of very old artifacts or human remains or fossils and other things. So, and that is because of the very large half-life of carbon-14. For other elements or isotopes, the half-life is different. It could be minutes, it could be seconds. It just happens that for carbon-14, it's a very long period of time. So we use the ratio from one to the other, and I want you to notice how the ratio first is mentioning carbon-14 here. So this will be the carbon-14, and then here this will be the carbon-12. So now we're going to go to our problem, and it says, to estimate the age of dead organic material, scientists use the following formula, which denotes the ratio of carbon-14 to carbon-12 present at any time t in years. So you could see that same ratio that we discussed earlier, it's there as well. So again, you could see on the graph, it is going to be decreasing. And so it says the graph of R is shown on the right. And so as t increases, t as the years, the independent variable, R decreases. And that is why we refer to it as exponential decay. So I noticed that the question is missing. Sorry about that. So the question is, estimate the age. I'm going to type it. Okay, so I typed the question. It says, estimate the age of a newly discovered fossil, which the ratio of carbon-14 to carbon-12 when it was found is equal to R equals 1 over 10 to the power 13. So what we're going to do to solve the problem to find the age, and I can tell you right now it's going to be 19,000. That's the age of the fossil. You can see it here on the graph. So what we do is we take the model and we substitute this R with the 1 over 10 to the power 13. So that's what I'm going to do. Substitute that with 1 over 10 to the power 13. and then the rest will remain the same. And what we're looking for is actually the value for t, because we want to estimate the h. All right, so first thing we're going to do is take the 10 to the power 12. We're going to take it across the equal sign. So you can see here on the right side it is dividing to the e because it's in the denominator. So if we take that across, we're going to have 10 to the power 2 times 1 over 10 to the power 13. And here on this side, we're going to have e to the power negative t over a to 3. Okay, so the left side, if we multiply here, we'll have 10 to the power 12 over 10 to the power 13. In this case, well, divide it on the next step. And then here we'll have e to the negative t over 8,223. So what we could do here with the tens is we could divide them. So we will be, in fact, let's just do this. So what we will do is subtract. So it will be 10 to the power 12 minus 13. That's what we're going to do right here. And so that will give me 10 to the power negative 1. Then on the right side, I have e to the negative t over 8,223. So now what we could do is take the natural log on both sides of the equation, because we want to get, we want to somehow cancel e. So here's ln of 10 to the negative 1, and then ln of e to the power negative t over 8,223. So you know that ln is base e, that cancels out. And this is gonna allow us to make the negative t over 8,223 will be not an exponent, will be a linear quantity. And then on the right side, we just have natural log of 10 to the negative 1. So one thing we could do here is take the 8,223 that is dividing on the right side. We take that across and the equal sign, so it will be, and in fact, I want to do this. I want to take this negative and assign it to the denominator. So then it will be negative 8,223 times the natural log of 10 to the power negative 1. And that will give us the value for t. Another thing we could do is, Tommy, we could use the power property, so that negative 1 will be here in the front, like a coefficient of the ln 10. And so here we will have a double negative multiplying. So then this will be positive 8,223 times ln 10 equals to t. And what we will get from there is approximately 18,934. So if we round it to the nearest year, or not the nearest year, but the nearest thousand year, it will be T will be rounded to 19,000. So that's the age of the fossil. Another very common question with half-life will be to find the amount after certain years. And also you could be asked like, and how many years will this turn into half? So here we have another example. It says determine the value of B in the exponential decay model that we have here. So we need to find B. Determines the decay of radioactive isotopes. For instance, to find how much of an initial 10 grams of radium isotope 226 with a half-life of 1,599 years. So that's almost triple as the carbon-14. So here's another element, and then the 226 is the type of isotope. So you start with 10 grams. That is the original amount. And then you want to find the constant that we need to construct our model. For example, with the previous problem, we had the model here. This was our model. So what we need to do here is use the information that we have. So we know that and in fact, the letter A that you see here, that is the initial amount. And so you can see that substituted here, 10. And then we have the rest. So negative, well, T, in this case, T is going to be the half-life that we have here. So you can see that number being substituted here. So instead of T is the half-life, and it is 1,599. Then remember that we're looking for B. That's what we're looking for. And what else do we know? Well, that it will take those many years for 10 grams to be half of 10. And so half of 10 is 5. We know that. So we could either substitute this with a 5, or just for, I don't know, I guess to show you, they're using half of 10, but let me just do it. So we use a 5. Oh, and by the way, that is the final amount. I forgot that. So the output is the final amount, or the amount after so many years. So remember, T is the independent. So the amount depends on the time. So then for the final amount, it's 5 because it's half. Since the half-life is that, we want half of 10 grams. So then this will be a 5. So from there, we have e to the power negative b times 1,599. Okay, so first thing, we divide by 10, obviously. And then here it disappears. Not disappears, but it cancels out. And so 5 over 10 is actually 1/2. So I'm just going to replace that. So 5 divided by 10 is 1/2. And what we do now is we take the natural log on both sides. So it will be natural log of 1/2. And then here on the right side, natural log of e to the power negative b times 1599. And in fact, I'm just gonna change the order here. So it's gonna say negative 1599 times b. Okay, and we know that here the base is e, so that will cancel out. So then we have a linear quantity. Negative 1599 times b is equal to the natural log of 1/2. So from there, to solve for b, we know that the negative 1599 is multiplying to b. So if we take that across the equal sign, it's going to divide. So we'll have natural log of 1/2 divided by negative 1599. So that will be the constant b, which is the decaying constant. And that's what we were told to find. And so that constant, oh, I'm gonna pause the video and find it. So the constant is approximately 0.00000 three zeros and then 433. So what the slide is using, instead of that number, they're using the expression that we have here. And that's what you could see here. So that's the constant b. Going back to our model, it will look like this. The final amount could be found by using the initial amount, which was 10, times e to the power negative. And here I'm just going to write it with the approximation. Negative 0.000433 and then t. That will be the model. And so the question here, it says, after you find b, it says the amount left. Okay, yeah. So what will be the amount left? The question is here actually. 500 years. What will be the amount left after 500 years? Let's look at the question again. And so that's why they're substituting here in place of t with 500 years. So just 500. And the negative that you see here is part of the model because it is exponential decay. So if you enter all of that on the calculator, or if we were just to replace this t here with the 500, you will get approximately, for your answer, you will get 8.05 grams. So think about it. The initial amount was 10 grams, and it took, so here's the initial amount. It took 500 years for those 10 grams to decrease to 8.05 grams. So not even half, like 20% less in 500 years. And that was radium, yes. Okay, so in chemistry, this is a very common topic, half-life. So you will, if you take chemistry, you will definitely be using the equation. Okay, so the next model that we will look at is the Gaussian model. And as mentioned at the beginning of the section, Gaussian models are of this form right here. And in probability, so you don't only have x as the exponent, the independent, but that will be squared too. So in probability and statistics, this type of model commonly represents populations that are normally distributed, and the graph of a Gaussian model is called a bell-shaped curve. And so it says here, try graphing the normal distribution with a graphing utility. Can you see why it's called the bell-shaped curve? So we went over some of this. You do get something that will be symmetrical, and that's a characteristic, of course, of normal distributions in statistics. Okay, so here, for standard normal distributions, the model takes the form of, and we have it here. So the average value of a population can be found from the bell-shaped curve by observing where the maximum y value of the function occurs. So the x value corresponding to that minimum y value of the function represents the average value of the independent variable, in this case x. So if we had the value that we have here corresponding to the maximum, oh, I think I said the minimum earlier. So the x value, let's say at a 50, let's say a 60. And so this is the, just like with the vertex, the maximum value, the maximum y value is here. So the x value that corresponds to that maximum value represents the average, or we call it the mean, which will be 60 for the example that I'm giving you. And this is the independent variable. All right, so if we go to example 4, we're going to be using this concept. And it says in 2011, the SAT scores for high school graduates in the United States roughly follow the normal distribution given by, and we have the model here. So that is a normal distribution. And the scores, which is the input, in this case we're using the variable x right here, that's the score. They go from 200 to 800, including 200 and 800. You could see those are actual points here. So our lowest score was 200, our highest score was 800. And we have the model here for that distribution. So it says where x is the SAT score for mathematics, and then it says sketch the graph of this function. From the graph, estimate the average SAT mathematics score. So the graph of the function, you see it on your right, and it is a bell-shaped curve, and the maximum value represents the average score. So right here is the maximum y value and the x value that corresponds to it, which is right here, is going to be 514. So that was the average score for high school graduates in 2011. Now the next model is the logistic growth models, and some populations initially have rapid growth, as you could see here, So it's increasing rapidly, followed by a declining rate of growth. So the next part that I'm going to highlight, it's still increasing. However, it's not increasing as fast as the part in blue. So it's still growing. It's still a rate of growth. It's just slowing down. Kind of like what the government was talking about doing with um, the number of infections of COVID-19. So to flatten the curve. So that is the logistic curve. And I tell my students that it's kind of like if exponential and a constant function had a baby, and so it would be the logistic function because eventually it starts leveling and it looks like if it was constant. So the function, the model for that is going to be here. And we have that y is the population size right here, the output. And here in x is representing the time, where they're not using t, but we'll have x. So an example is a bacteria culture that is initially allowed to grow under ideal conditions and then under less favorable conditions that inhibit growth. So for example, when you leave your food outside the fridge, you will have bacteria growing, and perhaps when you put it back in the fridge, it will not grow as fast because it's cold in the fridge, but you already have bacteria growing. So it will slow down, but you will still have bacteria growth. So the logistic growth curve is also called the, I cannot pronounce this, sigmoidal curve. Yeah. So we have a very nice example now. The spread of a virus. So it says on a college campus of 5,000 students. By the way, this constant here, this constant is going to be kind of like the horizontal asymptote of the logistic function, kind of like a limit of how high it will get, the output, how big would it be. So if we have a college campus that has 5,000 students, the biggest number of students that could be infected is 5,000 because you only have 5 students. So one student returns from vacation with a contagious and long-lasting flu virus. So the spread of the virus is modeled by, and then we have our model here. So as you could see, the number of students, 5,000, that will be here. And then we have that t must be positive because we're talking about time, the time after this person came from vacation. So where y is the total number of students infected in so many years. And now we're not using x, we're using t, but remember that is the independent variable, t for time. And in this case, t is in days, as you can see here, not in years, not in months. So the next sentence says, the college will cancel classes when 40% or more of the students are infected. So 40% of the students, and we want to find a percentage, so we could say that 40% of 5,000 students is going to be 0.4 times 5,000. And that would be equal to 2,000. So less than half. So part A of this problem says how many students are infected after 5 days. So after 5 days, you could see how T is being substituted with a 5 for 5 days down here. And so if we enter all of this on the calculator, you could enter something like this: 5,000, division key, and then you want to use parentheses to enclose the denominator, and then you continue, type in your numbers. So try it out with your calculator and then compare it to that's the time symbol, compare it to the answer that I'm going to give you. Or you can put parentheses here. Something like that. And then you want to close the parentheses to enclose the denominator. So if you enter that correctly, you will find that it is approximately 54. So after 5 days, 54 students were infected. So let's see. Part B, question B says, after how many days will the college cancel classes? So here the question is T. What is T equal to? The previous question, we had to find the output. How many students will be infected after 5 days? Now we have to find the time. And we know that the number of students that will be infected is going to be Y. And remember, it said that they will cancel classes at 40%. So Y is going to be equal to 2,000. So if the model goes like this, what we're going to do is replace the 2,000 or the Y with the 2,000. And then we're going to solve for T. So 2,000 here. Then we have this here. And so I'm going to take the denominator from here. And so it's going to be multiplying here on the side. And from here, we want to solve for T. That's our goal. So we're going to have to do everything that we can to isolate it. So first thing that makes sense to do is to divide by 2,000 on both sides. So you already know it will cancel on the right side. On the left side, I should say. And so on this side, we will have 500 over 2,000. I could divide by 100, so it will be 5 over 20. And 5 over 20, I can simplify it. If I divide by 5 top and bottom, it will be 1 over 4. Or we could even just use 2.5. If you enter on your calculator 500 divided by 2000 and you get a decimal, it will be 2.5. Okay, so now we are going to take the positive one from here across the equal sign. So now we will have 4,999 e to the negative 0.8t equals 2.5 minus 1. So that is equal to 1.5. So from here, what we're going to do is take the coefficient of e, the 4,999. You already know that is multiplying to the e, so we're going to take it across the equal sign and it's going to be dividing. So now we have e to the power negative 0.8t is equal to 1.5 over 4,999, and we're just going to leave it like that as a fraction. So next thing is going to be to take the natural log on both sides. And we already know it's going to cancel here, so we just have negative 0.8t equals natural log of 1.5 over 4,999. And so t is going to equal to the natural log of that fraction divided by negative 0.8. And so t will equal to approximately 10.1. And so it will take, remember that was our question, what is the time that it will take for 40% of the students to be infected? 40%, we found it was 2,000. So it will take 10 days for 2,000 students to be infected. So after about 10 days, maybe on the 11th day, at least 40% of the students will be infected and the college will cancel classes. So I think you can all identify with this problem a little bit. Okay, so the last example, yes, it is the last one, I promise, is the magnitude of an earthquake. And I mean, there are other applications. One that I find very interesting is Newton's law of cooling. You can determine time of death of a person. So that is a logarithmic equation. But here another example of an application of a logarithmic function will be the Richter scale of an earthquake. And so we use capital R as our output, and that is the magnitude of an earthquake. And I know that you have heard maybe on the news when there's an earthquake, there's always a number that comes attached to it, and that tells you if it was bad or not as bad or devastating. And so in Alaska in 2012, there was an earthquake with a Richter scale of 4.0. And in New Zealand in 2011, there was one with a Richter scale of 6.3. So I believe the highest scale will be 10. So to give you an example of earthquakes, there was one in, I'm trying to find a current one. Okay, so there was one in Indonesia, September 12 of 2007. It measured 8.5, 8.6 on the Richter scale. So I found that the highest register it was a 9.5 magnitude, and it was in Chile, or Chile, whatever you want to call it, South America. And that was in the year 1960. In the year 2012, that's not too long ago, I don't know, there was one off the west coast of northern Sumatra, and that was 8.6. So, yeah, those are pretty high Richter scales. Okay, so moving on. Here, the variable I sub 0, you see the subscript here, it is representing minimum intensity, and it equals to 1, and is just used for comparison. Now, we're going to find the intensity of each of these two earthquakes. So what we're going to be finding for is capital I without the subscript. And what they are giving us is the scale. So if we substitute for the first earthquake, the one in Alaska, so I just remember to give you an idea. On March 26, 2020, we had an earthquake that was between the cities of Odessa and El Paso. And that earthquake was of a 5.5 magnitude. So this one from Alaska was, it had a smaller or lower Richter scale. So it was less intense. So going back to our question. To solve for it, so we substituted R with 4.0, or just 4. And we're going to be solving for capital I right here. So remember, the initial intensity that we use is just a 1. And what we're going to do first is to exponentiate each side. Here, the base, and I'm just going to rewrite it. So I'm going to use 4 log of I. The base, since we don't see one, we know that it is an implied 10. So what we want to do is have 10 and 10, and then here we have to the power of 4. That's to what we call exponentiate, and here the exponent will be this whole quantity, log of I. Now we know that the base is 10, so we cancel that out. We just have capital I, and that is equal to 10 to the power of 4, which will be a 1 with 4 zeros. So the intensity was of 10,000. And I don't have the units for that. Okay, then for the next problem, we have the other earthquake that was in New Zealand. I don't know if I spelled that correctly. Yes. So then we substitute the R with the 6.3. We do the same thing. Exponentiate, so 10 to the power 6.3 is equal to 10 to the power log of I. And this is base 10, so that cancels out. So I is going to be equal to 10 to the power 6.3, which it is approximately Oh no, it's not a 5. It's a 9. 9, 5, 2, 6, 2. I feel like I'm missing something. So it's something like that. 1,995,262 for the intensity. And let's see. So yeah, that is the only thing that we had to find. Note that an increase of 2.3 units, so from one earthquake to the other, there was an increase of 2.3 units on the Richter scale, from 4 to 6.3, and that represents an increase in intensity by a factor of 200. So from one earthquake to the other, it felt 200 more times more intense. So just because, I don't know, 4 and let's say 4.9 are not too far apart, doesn't mean that the earthquakes are exactly the same. So in other words, the intensity of the earthquake in Christchurch was about 200 times greater, as great as the earthquake in Alaska. And this is the end of the video. So I just came back to tell you that the intensity, I just remember, I do not know the units, but it is the intensity of the waves that are being caused by the movement of the tectonic plates. So that will be the intensity.